Good morning, good afternoon, and good evening, everyone. Today, I'm going to present our research on using carbon fibers to increase the thermal performance of phase change materials. This is a collaboration work by staff members from 2 research divisions at the Oak Ridge National Lab. Here is the outline. First, I will introduce the background and the challenges of this work. Then I will discuss the general mechanism to increase the heat transfer and our approach using carbon fibers. The experimental and simulation results will be presented, and finally is the summary. The left pie chart shows the space heating and cooling took more than 1/3 of the total building energy in 2010 in the United States. From the right graph, we can see the big daily periodic variance in electric load from midnight to noon, especially in the summer. Therefore, thermal storage at off-peak hours and release at the peak hours can meet the energy efficiency demand. At Oak Ridge National Lab, we developed the underground thermal battery for this purpose. The left picture shows a small-scale prototype. PCM cans were inserted in the inner tank to increase the thermal efficiency. Thermocouples were put to monitor the charging and discharging processes. As the temperature profiles on the right shows, the charging process was relatively fast, about 2.5 hours to complete, while the discharging process was slow, lasting about 4 to 6 hours. Here is why. The phase change always started at the PCM container or in charging and discharging process. Therefore, thermal barriers would be the solid PCM in the charging process and the liquid PCM in the discharging process. Since solids PCMs has higher thermal conductivities than liquid, the melting process is always slower. Therefore, our experiment and simulations will focus on the melting process. Also, from the table, liquid inorganic PCM has a high viscosity and it can be treated as non-fluid. The liquid organic PCM has a low viscosity and its convective flow will be considered. To increase the heat transfer rate, Q over T, in this equation, we can either increase the thermal conductivity K or the effective heat transfer area A. In most previous research, micrometer-sized particles, whiskers, and flakes were added in the PCM to increase the thermal conductivity by a few times. In our approach, thin and long carbon fibers with certain anisotropy were added in the PCM. The right graph shows that both isotropic fiber and the highly anisotropic fiber actually do not increase the effective heating area A very much. The heat either dissipated fast at the hot end or from hot end to cold end. A certain anisotropic fiber can release heat flux sideways along the fiber axis in a controlled way and could increase the A by 40 times in our experimental setup. Here is a simple 2D axial COMSOL model to understand the effect of the anisotropic of carbon fibers in heat transfer. This is a single carbon filament about 5 millimeters in length and 2.5 micrometers in radius. It is put in a frozen PCM at 4 degrees C. At 0 second, the bottom began to be heated up at 20 degrees C. The anisotropy of the fiber is defined as the K ratio, or the K in the radial direction over the K in the axial direction. The right graph shows the solid phase content along the fiber surface after 120 seconds. As we can see, the fiber with the K ratio 0.1 melt the PCM the most, and K ratio as 1 the least. Other anisotropies at 0.9, 0, or 0.5 are in the middle somewhere. So a carbon fiber with a K ratio 0.1 has the highest melting efficiency and was used in this study. Here is the experimental setup. The frozen PCM container was put in an insulated beaker of water at room temperature. 3 thermocouples at the center of the PCM, on the container wall, and in the center of the beaker of water were used to monitor the melting process. 1 weight % of carbon fiber were chopped into 1.4 centimeters in length and randomly dispersed in the PCM. Visual observation could only be made on organic PCM, and we can see the location and size of the solids in the melting process. The solid stays at the bottom in the pure PCM and in the middle with carbon fiber inserts. Here are the temperature profiles with and without carbon fiber inserts at the center of the organic PCM and inorganic PCM. For inorganic PCM on the left, the starting time can be approximated by the slower temperature increase. Carbon fibers led to slower temperature, and it was due to the fast phase change and latent heat release. For organic PCM on the right, with carbon fibers, the melting ending time probably is near the decoalescence valley. And the violent temperature change for pure OPCM is related with the solid-liquid interface passing through the thermocouple tip. Overall, the experimental data gave us very inaccurate and limited information about the melting process, and so we resolved the simulation for better understanding. Luckily, COMSOL physics have 2 modules of phase change materials for this study. The domain phase change module can be applied to inorganic PCM for its incongruent phase change with the melting range. And the phase change interface module worked well for inorganic PCM for its congruent melting with a fixed melting point. In IPCM, only thermal conduction is considered, and in OPCM, both conduction and convection are applied besides the phase change. For inorganic PCM, the simulation matched quite well with the experimental data for the temperatures at the 3 locations. From simulation, we can also see the temperature field and the phase change fronts move from the wall towards the inside the PCM. With carbon fiber inserted in IPCM, the model had to be in 3-dimensional, and the simulated center temperature also matched the measured data. For comparison, temperature field and the melting fronts at the center plane were shown. To quantify the melting process of IPCM, 3 properties were listed here to show the effect of carbon fiber inserts. The thermal state of charge is the percentage of the heat released over the total heat capacity, which includes the latent heat and also the sensitive heat of the system. As the left chart graph shows, with carbon fibers, SOC increase fast towards 1 and the solid content decrease fast towards 0. On the other hand, experimentally on the right, the water temperature with carbon fibers was 1 degree lower. All this show a higher thermal efficiency with carbon fiber insert. So in conclusion, for IPCM, carbon fiber enhance the phase change and latent heat release. For pure OPCM, the interface model worked well, predicting the center temperature profile. Also, from simulation, the solid content, which is marked by the red zone, and solid shape and locations are shown here. From simulation, the convective flow development can be also described. With carbon fibers in OPCM, the solid-liquid interface around the fibers is too complicated for simulation, and thus a domain module is used. And the results were fairly good at the later part of the melting process. The simulated solid phase shape and locations are very close to what we observed in experiments. The same methods can be applied to quantify the melting process for OPCM. As both simulation and experimental data show, the carbon fiber did not make much difference in this setup. The carbon fibers increased the conduction but reduced the convection, resulting the close SOC lines and water temperature profiles. Here is the summary of our research. First, both high thermal conductivity and a certain high anisotropy contribute to the fast phase change and latent heat release. Second, for inorganic PCM, where only thermal conduction is present, carbon fibers increase the thermal efficiency. For organic PCM, where both conduction and convection are present, the effect of carbon fiber is mixed, increased conduction and decreased convection. The total effects is depending on the system geometry. Thirdly, simulation helps understanding the melting process quantitatively and can help designing thermal storage system with higher thermal efficiencies. At last, we would like to thank Oak Ridge National Lab and the U.S. Department of Energy to sponsor this research. Thank you.